relations between these translational motion quantities and quantities in circular motion. That is, we are going to take some quantities, especially displacement, velocity and acceleration in translational motion, or translational motion means a linear motion, and in circular motion, the same type of quantities in circular motion. Okay, already we know that angular velocity, that is velocity there. Similarly, we are having angular acceleration, it is indicated with alpha, and ordinary acceleration in translatory motion. Okay, first we take quantity. This is relation between between translational and circular or rotational quantities. Relation between translational and circular quantities. We take quantity here, then translational motion, then circular or rotational motion, circular or rotational motion. In this one, quantity again. Okay, first we take displacement. In translational motion, we denote this one with S or capital S or X, like this. In circular or rotational motion, we denote this one with theta. This is angular displacement. This is angular displacement. Okay, this is the first one. The second one is velocity. Is V. This is omega. This is angular velocity. Or as it is rotating about a point, it is going to continuous its motion continuously on the same path. That is repeated motion. That's why we call that one as frequency. What is the frequency of bus from one place to another place means we will tell the rate at which it is going on. Okay, or it is called as angular frequency. Then acceleration. A. Okay, we indicate with half. This is angular acceleration. Okay, we are having these things, and we know omega is equal to C dx by dt, d theta by dt. A is equal to dv by dt. This is equal to d omega by dt. d omega by dt. Okay. d omega by dt. The rate of change of angular velocity is angular acceleration. Now we see the equations connecting these quantities. We know these quantities. Okay. First, the equation is, now we see equations. Equations for fourth one. Yes. For x. X is equal to S is equal to ut plus half at square, or x is equal to v naught t plus half a t square. Okay. Then for v velocity, okay, v is equal to v naught t, v naught plus at, v naught plus at. X is displacement during t time, which is having initial velocity v naught and it is moving with acceleration a. Okay, this is v naught is the final velocity after time t, the body for which initial velocity is v naught and it is moving with a acceleration. Okay, then equation for, we are going to have relation between v naught, then acceleration and x. Okay, we simply write this one as v square is equal to v naught square plus 2ax. 2ax. We know these relations. Similarly, from this analogy, we can write the equations for these quantities. X here is theta. Theta is equal to theta naught. Not. We will see that one later. V naught means omega naught t plus half, instead of a, alpha t square. Alpha t square. Here omega is equal to omega naught t. Omega naught plus a, alpha t plus alpha t. Then omega square is equal to omega naught square plus 2 into alpha into what is this one, x theta. But in general, for this rotational motion, if it moves, in general we are going to take like this. It starts from this point like this, and we mentioned our angle from the x-axis. But there is no need to start from this one. We can take any reference axis. That's why if the initial value is theta naught, then if the initial value is theta naught, then we are going to make some changes in these equations. Okay. For this one, if it starts from theta naught, we can write this one as theta is equal to, it started from theta naught plus our value omega naught t plus half alpha t square. That is, if it starts from theta naught, we have to count from that value, theta naught plus omega naught t plus half alpha t square. There is no value of theta here, we simply retain that one. Omega is equal to omega naught plus alpha t. Okay, Then the last one is omega naught square. Omega square is equal to omega naught square plus 2 alpha theta minus theta. Theta minus theta. Theta is the displacement. Okay. Then the displacement becomes theta minus theta naught. Okay. If it starts from theta naught. This is how we are going to write the equations in circular or rotatory motion. Okay, these are the equations in circular or rotational motion. These are the equations in translational motion. Okay, we just take the quantities, translational motion, circular or rotational motion, then a quantity in this motion. Okay, in this rotational motion. Already we know these equations. Okay, the similar types of equations are written in for rotational or circular motion. They are simple to remember. Okay, by just having this analogy, we can write the equations in circular or rotational motion. We have to remember these equations.